All right. Hi everybody. Today we have Joel Schlosser, who's going to talk about how Torch Compile can achieve state-of-the-art performance for Flux image generation. So take it away, Joel.
Hi, everyone. Yep, as you mentioned, I'm going to step through a series of optimizations on the Flux model and just demonstrate some really good state-of-the-art results we've seen and show kind of within traces like what's going on as we apply these techniques. So I'll do a quick summary of the optimizations that we're going to look at, and then I'll dig in deeper on each of these, how to apply them in code, and then I'll look at the traces. So just quickly, bfloat 16. Obviously, applying torch compile, doing some projection fusion, using channels last memory formats, flash attention v3, some dynamic float rate quantization, um, some inductor tuning within compile, and then finally this export AOTI and CUDA graphs combo for the final fully optimized version. Note that all these optimizations are lossless. There might be some minor numerical differences with compile, but in general, this is lossless. The only exception here is float rate quantization, of course.
Hmm.
So, quick like demonstration of what this looks like. The baseline model with a cat playing with a ball of yarn prompt looks like this, and then the fully optimized version is not too much different. You can see a little bit less detail in the fur. This is with quantization. And if you want, again, like the exact same output, you can disable quantization and
Hmm.
still get rapidly improved results, but without any loss in quality. Cool. So then uh, quickly, I'm going to introduce like what I'm using here. So this is all pure PyTorch native techniques, also relying on torchao. We're going to use the diffusers library for the Flux model. And then Flash Attention 3 is a separate library, is currently required. Eventually, this will be provided through PyTorch, and we're working on that now.
Okay.
Okay.
2.8 is releasing soon, so we'll have these fixes in that, right?
Um, it may be bumped to 2.9, but we'll see what
Okay.
I can do with Driss. So, yeah. Okay, so starting out, I'll just show how to use the diffusers library to get the Flux model working, and I'll show the baseline trace. So it's very simple to run this. I just import Flux pipeline from diffusers, load this pre-trained checkpoint from Black Forest Labs, and we're using the Schnell variant here, which is the fastest one. It's lower in quality than Dev or the newly released context. Um, but it's the fastest. And a lot of these optimizations also apply to those other variants. So eventually this will be updated to show results for those as well.
Mhm.
But anyway, so here's where we take the prompt, run it through the pipeline, and we get an image out. Very simple. Um, and then I will pull up the trace here. So can you see this okay?
Yeah.
Okay, great. A few things I want to point out in this trace. Top is CPU, bottom track is GPU. You can see the components of the Flux model, which briefly are prompt encoding, where we take a text prompt, run it through CLIP and T5 pre-trained models to get embeddings in the multimodal embedding space. Then we take those, we run it through a series of denoising steps. Here we're doing four denoising steps, and this is transformer based. So of course, a lot of matrix multiplications happening under there. And then finally, on the far right side, there's a decoding step to convert back into output image space. And then this post-processing step is simply bringing all that stuff from the GPU back to CPU, converting to a pillow image and outputting that to disk. So simple there. Um, as you can see, the most of this work required is in the denoising. So that's the transformer-based parts. And again, that's the dominant like GPU usage here. If you zoom in a little bit, you can see hopefully that the GPU has pretty good utilization right now. There's not a lot of gaps in terms of um, uh, whether we're like using the GPU or not. It seems to be pretty packed full, which is good. So this means that the use of CUDA graphs won't provide us like a huge speed up. And we're going to be focused on optimizing the matrix multiplications and doing fusions to reduce the actual like kernel runtime on the GPU. Um, okay, so let's see. Is there anything else I want to point out here? I think I'll point out also, you can see all these individual CUDA launches here.
Mm-hmm.
Um, this is because we're not using CUDA graphs in the baseline model. Uh, but again, the CPU is kind of ahead of the GPU, which is what we want. We see a bunch of launches, and we can see that the CPU can continue. With one exception here, there is a sync point, this non-zero call during the first step. And I don't want to get into too much detail on this, but I have an upstream fix to diffusers to get rid of this sync point.
Ah.
Um, yeah, so that any like minor time difference that causes this GPU gap here, which is more pronounced in the compiled traces, as we'll see, that will be fixed upstream in the newest diffusers. Okay, let's see. So I think I did like an overview of what this trace looks like. We can kind of zoom in on what these map moles look like. You can see uh, they're pretty expensive, and you see the float 32 here. So I'll quickly go into the next step of um, running this in bfloat 16. There's never any reason really to run it in float 32. I think most people will run this model with bfloat 16. And it's very easy to get that with the diffusers code here. So you just load in bfloat 16. Um, Very quickly, you can see uh, if we zoom in on these, let's see, maybe, yeah, you can see some, looking for some bfloat 16 here. There's some bfloat 16 with the flash attention kernel. Yeah, so this takes it down from about 7.5 seconds in the baseline to now we're running in 1 second, 1.2 seconds.
Yep.
Um, Much faster.
Yep.
We still get these individual CUDA launches here, but that will go away as we apply compile. Um, so that's all I want to say about that. Then we'll move into compile. So the most compute intensive portions, as we pointed out, are the denoising transformer, and then the decoder is second here. So we will manually apply torch compile here to the transformer component, and we want to use the max auto tune mode to really make sure we tune those gems in convolution layers. And we want to make sure there's no graph breaks here for best performance. So we apply that to the transformer as well as to the variational autoencoder decoder.
Did you have to do anything to make full graph equals to true go through?
Luckily, the diffusers library has an extensive like set of tests that operate with torch compile to ensure there's no graph breaks. So out of the box, this
Mm.
already worked, which
Okay.
is nice.
Yeah,
Yeah. And again, if it's found that that's not the case for some model and diffusers, I think they're very happy to accept upstream PRs to fix that.
that's good.
Okay, so we'll do a little bit of warm up here to trigger compilation and then run the model here. And the trace for this is here. So now you can see that the denoising steps all are launched within CUDA graphs and this along with the uh, max auto tune mode is providing us with a decent amount of speedups. Now we're at 766 milliseconds, down from 1.2. So here's just some output of what this kind of looks like here. As it does the auto tuning, you can see the max auto tune mode is identifying these matmoles of different shapes and then trying out different kernels to see what performs best for those shapes on this hardware, which I should mention is an H100 96 gig GPU.
How long does this auto tuning take?
This auto tuning can take a little while. I would say on the order of like, 30 seconds to 2 minutes, somewhere in there for this model. But it's cached, so you only have to run it, the first time. Yeah. And then it will store all these results out and use that for the next time. Uh, I guess one interesting thing about the matmos here is that we're generating a bunch of Triton templates with different block size hyperparameters and picking the one that performs the best for these. So with this process in play, we've achieved some good speedups. And I think if we had seen worse GPU utilization, then the CUDA graphs would have helped as well. And then the final thing I want to point out here is the sync point here actually matters a little bit. You can see there it is, the device to host sync for the non-zero call. Oh, sorry, I won't. Yeah, there we go. This matters now because we have to load the cache, the Torch Dynamo cache lookup from Torch Compile. So having the CPU wait here for the result of the non-zero call is not ideal because now we're incurring the cost of this cache lookup. And
Mm.
that's what this GPU utilization gap comes from. So again, this will be fixed upstream. Okay, so let's see. Is there anything else to talk about for this? I think it's all fairly straightforward. We got our CUDA graphs. The CPU is mostly ahead of the GPU, which is good. And we're getting very good speedups from both the fusions and the matmul and convolution tuning that's happening with max auto tune mode. Okay, so let's move on to the next set of optimizations, which is doing combined attention projection for the attention components. So rather than doing individual projections for a query key and value, we combine this into one large matmul, which generally performs better. Um, Diffusers provides like a nice way to do this, just using fused QKV projections. So that's the way to apply here. The, Interestingly, we don't actually see speedups for this that are no outside of like noise. So if you look at the results in the graph, the compile bar here and then the QKV projection bar are about the same, is because compile can actually identify this automatically and perform those fusions. So there's no need to do the separate diffusers based thing if compile comes into play. So that's all I want to say about that one. We'll move on to channels less memory format. Um, so the idea here is to set the output of the variational autoencoder to use the channels last memory format. Um, the idea here is that rather than representing images in the form of NCHW, batch size by channels by height by width. We'll do batch size by height by width by channels, putting the channels at the very end and improving like locality. There are also some more optimized kernels for operating on channels last. So in practice, what this looks like in the trace.
So, question,
Oh yeah.
is this something that Torch Compile also auto-tunes for, or seems not?
There is an option to do that based on a comment from Elias. If you turn on inductor freezing or you freeze the weights, it's able to flip the memory format automatically to what's optimal. But that's not on by default right now.
Okay.
Yeah, so let's see what this looks like after here. Uh, One thing I should probably talk about in the post-processing step, the final component is converting to the pill image. So I have this annotated here, pill conversion. You can see it's taking 20 milliseconds. Um, then after we apply channels last, that component shrinks down to 7. So some like 13 millisecond savings out of the total of 742. It's not nothing. It's something. And the reason for this is because having the output in channels last format makes the pill conversion much more optimal because pillow represents stuff in the channels last format. If it doesn't see it coming in that way, it'll convert it, and that conversion is not free.
Yeah.
So that's where we get most of our savings from channels last year. Okay, so then now we're down to yeah, we shaved a little bit here. Looks like 13 milliseconds between compile and channels last. Now for some bigger optimization. So flash attention v3 will apply next. And this is known to give very good speedups on H100s. Um, Part of this is because it now has float 8 support. And this gives very good gains. So this isn't quite available yet in Core as we mentioned earlier. So I implement a custom attention processor. Luckily, Diffusers provides this interface to do so fairly easily. And then I use the flash attention interface kind of directly. If it's interesting to you, I can step through what this looks like. I don't know what you think.
I see. Yeah, so it's cool. So you can basically swap out the attention processor.
That's
Yeah.
right.
Okay.
Yeah. And this is pretty straightforward. So I had to here I'm importing the flash attention interface. This is flash attention v3, the beta, and then I'm calling the function manually. And I'm calling it with kind of an unscaled float 8 conversion on the inputs. And this provides very good speed ups, as we'll see. This is wrapped in a Torch library custom op, which allows it to iterate with Torch compile. And then as part of that, we have to register a fake implementation. So we have uh, this quick meta function here that returns a meta tensor in the correct shape as the output, which is fairly easy to get. Then I call this op from inside this attention processor. So this attention processor, I just shamelessly copy pasted from the old version. And then I swapped out one call here, which is right here, where I'm using my custom op on the query key and
Gotcha.
value.
Yeah.
And the transposes are necessary to match SDPA, which used to be here. So this used to call SDPA, now it calls Flash Attention 3 directly.
Mhm.
Yeah, so that's what's going on there. And then we set attention processor with that custom attention processor, run compile as before, and we can take a look at the trace here. Uh, Here we go. So now we're down to 633 milliseconds. I think previous iterations around 720 in this. We still have the small gap here. It's okay. We'll zoom in. We can see usage of the Cutlass Flash Attention 3 kernel, which if you compare to previous, it's much faster. It's operating on somewhere in here. It should be obvious that it's operating on float 8. Let's see. Uh, I have to find the right one. It's kind of hard to do, but somewhere in here. Hmm. Anyway. Oh, here we go. You can see float E4M3. So this is the float 8 data type. So we're taking advantage of that very fast flash attention 3 for attention. Okay, I think that's all I wanted to say there. Uh, Next, we'll look into some lossy optimizations. So from torchao, we're going to bring in dynamic float 8 quantization, and we'll apply that using the quantize underscore
Mhm.
API from torchao, which will in place modify the transformer,
Mhm.
and it will perform dynamic conversion to float 8 for the weights of the linear projection layers within that model, as well as the output activations throughout. And this gives us a nice speed up as well. So if you look at the chart here, we go from 0.624 in this bar down to 516. So it's a pretty substantial
Okay.
benefit here.
You only apply it to the transformer?
That's right. So the reason for that is because the variational encoder is mostly comprised of convolution layers. And so in practice, there's not much speed up from applying it there. You could, but I didn't see much difference outside of noise. Um, yeah. So let's see.
So that got us to okay, half a sec, half a second.
Yeah. Yeah. So we can zoom in and we can see where, um, I won't try to find it, but in here you can see the flow date happening. And then yeah, as we optimize this gap becomes a little more substantial here.
Mhm.
Uh, so
How
there's
much
that.
was that gap? Just in terms of
Oh yeah, we can measure it here. I think it's on the order of 17 milliseconds or so. 16.6.
okay.
Yeah, so that's like substantial. That'll go away. Um, but yeah, we're getting pretty good here. We're down to 520 in the trace, and yeah, nearing half a second. Um, all very easy to apply optimizations. Uh, Yeah, I mean, you could potentially play around with this in other areas, but this is definitely the most computationally heavy. So applying quantization here. Uh, Finally, we can mess around a little bit with how Inductor does its tuning. So in practice, like this gives us a little bit, and I think there's these options are changing pretty frequently. I think the next thing I want to play around with that's not quite available yet is additional like matmul related tuning settings, bringing in cutlass based templates and stuff like that. But in what I'm using here is I'm treating one by one convolutions as matmuls to get those like highly optimized kernels. I'm changing the auto tuning algorithm for max auto tune uh, to check like a broader grid search here.
Hmm.
Uh, and then I'm in practice, I found that turning off epilogue fusion gave better results, and I really should dig into that. But it's an option here, so that's what's going on there, and that gives us a little bit of squeeze out a little bit here, which
Interesting.
going down from float 8 to here, so it squeeze out another zero point zero 0.01.
So
And we,
that's, yeah, that's a little surprising. Like,
it is, I agree.
are there any kind of high level theories on why that might happen? Even if you haven't confirmed that they're true.
Yeah, that's honestly a great question. It's one of the biggest gaps in my understanding for this work that should probably be dug into. I don't have any like real theories here at the moment, and you could argue that this is noise, but I think 0.01 seconds is like pretty reproducible, so it's maybe just outside of that.
Okay. Could it be that so when we are doing auto tuning, we are doing it in general, like is it like when we are picking the best out of multiple options,
Yep.
um do we take into account epilogue fusion in general?
Oh yeah, that's a good question. I'm not aware that we do. So I wonder if that could be playing into this.
Yeah, so that's kind of making it make a suboptimal overall.
Yeah, I think that's a reasonable theory. This definitely needs to be dug into.
Okay.
Okay, so yeah, that's what I've done there to kind of tune Inductor a little bit. The biggest step here, I think, is this final one, which is applying export and AOTI. So as of now, we've applied compile with all these optimizations, and we incur that initial compilation time. Even with the cache, it's still somewhat substantial. So we want to, ahead of time compile, serialize this, and make this loadable. And that's what export and AOTI here provide. So this is a little more involved, but I'll step through this on what this looks like. And this does, uh, when combined with manual CUDA graph usage, it does bring this down slightly more here. As you can see in the fully optimized trace, that gap is gone here. And the torch dynamo cache lookup gaps are gone as well. So this gets us down to just under a half second in the trace. Um, cool. So let me step through what this looks like. Okay. Uh, Here I have well, let me start with the bottom here. So same as before, and then I have this use export AOTI call, which with a cache directory. So I'll show you what this looks like. This involves let's see, the important part is this call here. So this is the export call. We're running that on the transformer. We pass it a set of representative arguments here. And this is in practice what I've seen the transformer accepts. I create example tensors on the correct device of representative shapes for each of these inputs, and then pass that along to export. And then this gives us an exported program out. We can then pass that into AOTI. So this is currently private. And I think being figured out how this is going to be exposed. But the idea here is, we take this unoptimized exported program and then do ahead of time compilation and serialize all those kernels and such into a
So
binary.
at a high level, so you mentioned a bunch of torch compile oriented optimizations. So
Mhm.
a- are we doing this on top of whatever we did before, or is this going to basically recreate the results of the torch compile?
Yeah, this here will apply all of the torch compile based optimizations, this step here.
Okay.
So everything as we did before.
But you didn't, your inductor configs are fewer.
Oh, I'm sorry. The inductor configs should be still the same
Oh,
inductor.
I see. Okay,
Yeah.
okay. So you've
Excuse
already
me.
done some settings and then you're like,
Yeah.
I-
We've done some settings and then when we get to this point, we'll do the ahead of time
okay.
compilation.
Makes sense. Makes
Yeah.
sense.
So yeah, that's what it looks like here. We'll apply AOTI, use max auto tune in the config, and serialize this out. I guess the serialization is maybe not shown here, but uh, oh wait, yeah, it is. Yeah, the AOTI compiling package will output to this decoder package path, so that actually writes out a binary that we can then load later, and that's what we'll do here. So we'll load the package here, and this run single threaded call is important and kind of interesting. So what I'm about to talk about after this is manual application of CUDA graphs. So when you use export and AOTI, yeah, and you load the model, you do not get CUDA graph support out of the box. You have to kind of apply that yourself, do the record and replay stuff. Um, and that actually does uh, interact badly with AOTI if you don't pass this run single threaded call. So there's some threading machinery that conflicts with CUDA graph usage, and you avoid that by passing this flag here. So this is important. Okay. Then we will, let's see, do some warm up and we'll apply the CUDA graph layer, which I will talk about now. Also the same thing for the variational autoencoder decoder. But the CUDA graph thing is interesting here. So again, we without this, you kind of I've seen like a 5% performance decrease versus the torch compile,
Okay.
and I want to like reduce that gap here. So I just manually record and replay the CUDA graphs over this to get rid of that gap. So this wrapper here automatically handles doing CUDA graph record replay, does some magic. I guess the key aspects here are here where we create a new CUDA graph and then where we call the function with the given arguments into that CUDA graph and record it there. And then we do some caching. So this underscore graphs here will cache this for this set of input arguments. It'll cache the recorded graph. And then next time we call this, we can just pull it out of the cache and, or sorry, pull it out of the cache and call that CUDA graph. Now, CUDA graphs require the inputs and outputs to be in fixed memory locations. So in order to actually use this properly, so we want to make sure that in the CUDA graph that we've recorded with those fixed input and output locations, any new inputs that we're trying to run through the CUDA graph are copied into those locations.
Mm-hmm.
So that's what's going on here. You can see we're copying the new inputs into this like sort of fixed memory location that we then use in the CUDA graph when we do the replay. And on the output, the same sort of thing. We want to clone these so we don't get like overwriting from running the CUDA graph multiple times.
I see. So how gen this code looks completely generic. Is this something that we should provide as an API, especially if it's more of a design thing that you have to do that single thread thing,
Mhm.
flag, and then you have to do CUDA graphs manually.
Yeah.
Either
Yeah.
we fix that situation, which maybe it's by design, or we have an API that just does.
Yeah. I think that's a good point. I think a good argument can be made that we should provide this generic API for sure. Now, there is some like overhead here with the initial recording, and potentially you might want to structure that differently. I don't know, but I think as far as applying this wrapper directly to a function and having it handle record replay for you is pretty nice. So yeah, I think you could argue that we should provide this. Okay. If there's, let's see, no other questions there. I think that covers export ATI and the manual CUDA graph layer. And then, the final trace again, for just under a half second. And then you can see the actual CUDA graph launch calls here so that we know that our recording and replaying actually did work. Um, yeah, and then I guess generally reduced overhead from not making the cache lookups for compile.
Hmm.
Yeah. So yeah, I think that is pretty much it.
Very cool.
Yeah.
So the savings between compile and AOTI are exactly the time you saved by avoiding cache lookups.
Yeah, I think that's about right. Yeah.
That's okay.
Yeah.
Yeah, this is really really nice. It was kind of fun watching like the progression of things. Like every little optimization feels like yeah, it was necessary for a different purpose. So it feels like okay, they combine well. They're kind of like orthogonal, except for maybe one or two of those at the
Yeah.
beginning. Yeah.
Yeah, that's right. Yeah.
So another question I have is sort of like this is a recipe. Like I think some parts of it were maybe specific to this model, but mostly it felt like a recipe for speeding up transformer based things. Like
Yeah.
how much of it was driven by you looking at the profile versus something that is again maybe a little generic, maybe because if people do not know about all of these things individually, they just want
Mhm.
to try something. Is it possible to kind of create an optimization pipeline that that would apply these things?
Yeah, I'd say so. I think, like you said, this is kind of just you run through the recipe and apply all these things as needed. And if it's a transformer-based model, you will benefit a lot from what we know are components of the transformer, which is like minute moles and attention and all that, and improving that. So yeah, I think this to some extent is fairly generic. As long as you pass this sort of thing. A model that involves a transformer, which in this case, the model specific part is that it's called transformer underneath the pipeline.
Yeah.
But otherwise, all this stuff could be done kind of generically.
Yeah. You could
Yeah,
even ask the user to pass in what the transform bit was
yeah,
and focus on optimizing that part. Yeah.
exactly. Yeah. So I think providing this as a generic recipe for transform-based models would be really useful. And then, we can there's maybe some empirical playing around with some of these inductor flags that might come into play, especially as new like settings come out and we're playing with those. But that could be dependent on the input shapes or whatever, and that's kind of model dependent. But otherwise, I think yeah, a lot of this is very generic.
This last line of max auto-tune jump backends, you only have that to add Cutlass to the mix, is it?
That's right. Yes. So currently, Cutlass is not
Yeah.
on by
Okay.
default, and this is yeah.
Lazarus just recorded another video with me the other day,
Oh,
and
great.
which order these will come out eventually. But yeah, he was talking about the Cutlass backend.
Great. Yeah, my understanding is he just landed a decent amount of that support, and it's fairly early stages, but I want to try it out here as well.
All right, nice. Uh, yeah, thanks, Joel. It was pretty nice.
Sure, sure thing.
Okay, we'll end here. Bye bye.
See ya.